So the exact same thing happens with molecules. So magnets that you can see, the same ends repel, opposite ends attract, and they stick together. Well, if all these magnetic things stick together, then things that are not magnetic are going to get shoved out of the way. There's no reason for them to stick to the magnets. And so what ends up happening is if you have a big jar full of things that are magnetic and not magnetic, all the magnetic things will stick together into one big lump, and the non-magnetic things will be left out in the cold. This is exactly what happens with oil and water. Water is like a magnet for itself, for other molecules of water. They stick together, and then they make one big lump of liquid in like your oil and vinegar salad dressing or Italian salad dressing that you have to shake up. The oil gets left out. It doesn't stick like a magnet to anything. It has no magnetism. It has no polarity. And so what ends up happening is the oil and water will separate. The same thing happens with milk. If you get it straight from a cow, you can pasteurize it to make sure there's no bad bacteria in there. But if you've done nothing else to it, then the cream will separate out and go to the top of the jar. The cream always rises to the top, is the adage. So the watery part, which has a lot of the sugars and other things that are in milk, you know, the lactose, is down at the bottom because all of those things are polar, they're magnetic. The things that are not polar, they're not magnetic, the fat of the milk that has the vitamin A and the vitamin D, that rises to the top. So if you have old-fashioned milk, again, you can pasteurize it, so again, no bad bacteria or anything. You have to shake it up, just like you have to shake up Italian dressing sometimes to mix those oil and water droplets. But after a while, they will separate out again because gravity doesn't stop working, and neither does magnetism. And those two forces are what explains so much of what happens with things that are allowed to move around. The solids, it's different. They don't move around so easily. Those molecules can't move. But the liquids can, and gases even more so. Now, what we breathe in air is mostly nonpolar. Think about the number one gas is an element. It's nitrogen. It does nothing in our bodies, except, you know, if we go deep sea diving with high pressure nitrogen, then it gets into our cells. And when we come back up to the surface, it depressurizes quickly and it rips out through our cells and causes the bends, or it can even be fatal. There's number two thing in air. Okay, air, which is another fluid just like water. Air has oxygen in it. That's another element. Both of these elements, by definition, have no difference of electronegativity. They have no difference in electronegativity. So therefore, they are nonpolar. The third thing in the air, carbon dioxide, at least in dry air, like in the winter or in the desert, is going to be carbon dioxide. And that also, because of its shape, even though there's a big difference between oxygen and carbon, and that could be polar, because of its shape, it will still not be polar. Because why should the left end be more negative than the right end? They're both equally oxygen. So even though there's a carbon in the middle, because it's linear, it has symmetric shape. And so because of the symmetry, there will be no polarity. No polarity. Another thing in the air, argon. Argon is a noble gas. It does nothing. It definitely does nothing. So the top four things in the air, in dry air anyway, have absolutely no polarity. But there is one thing in the air that is polar, and that is water vapor. Especially on warm, humid days, the water vapor in the air will interact with itself. It will stick to each other. And this is wonderful because we get the water cycle out of this. So that the sun's rays do make the water evaporate. But as it goes up and slows down in the air, it bumps into other water molecules and gathers together and makes rain. So we have rain in places where there are no springs. It makes life on Earth possible. One of the 100 or 200 things that have to be just right on Earth to make life possible. But back to the slideshow. I'm going to share the screen now. And let's see here. The covalent bonding. Does everybody see that?
Yeah.
Thanks, Nat. Okay, so just a reminder here: if you do the math, And by the way, the reason I'm looking off to the side is because I have this up on the projector so I can see you and also see it. If it looks weird, my face looks weird, just look at the shared screen and ignore my face. Anyway, the electronegativity numbers are not ones that you really need to memorize per se, like you need to know the atomic numbers. You absolutely need to know the atomic numbers and where these elements go. The electronegativity numbers are not as important. You can look those up. They're all over Google, DuckDuckGo, whatever server you use, search engine you use. So there's a difference here between nitrogen and hydrogen, 0.9. It's going to be polar. No difference in fluorine gas, non-polar. Calcium and chlorine, huge difference. It's going to be ionic. And then we had the ambiguous aluminum and chlorine, where is it ionic? Is it just strongly covalent? I advise you to consider that ionic, even though it doesn't match the rule of 2.0. For one reason, the other sources that I've used in the past draw the line at 1.7, so 1.5 is even closer to 1.7. But it's debatable. Is the point? It's in a gray area, and so there's nothing so good as an honest, open debate. So, but I advise you to consider that ionic because you do have a metal and a non-metal reacting together, and it likely forms a crystal lattice. Now, there are things that form crystal lattices, patterns, that are not ionic. For instance, water, when it makes ice, makes a crystal. It is not ionic. So just making a crystal does not mean it is ionic, but it's a good indicator that maybe. All right, now, again, they're saying here very polar covalent, but I'm saying let's go more with ionic. And I will go ahead and bold that. Control B, there we go. All right. So if you have a polar bond, then often the entire molecule becomes polar, but not always. Just like I mentioned with carbon dioxide, very, very common molecule, it is not going to be polar. So the polar molecule, the whole end, sorry, one end is negative, the other end is positive, just like a north and a south pole on a magnet. And I encourage you to play with magnets, these sorts of things, to just get a feel for what do magnets do. Get a couple of, kitchen refrigerator magnets that don't have a picture or anything on them, just pure the black circles or whatever, and play with them. Get some neodymium magnets too, but don't squeeze your fingers; those are hurt. So the word you need to know is if you have two, then it's dipolar, not bipolar. That's a different word. Dipolar. And so you can think of it as division. There's a division there. One end is like this, and the other end is like that. So hydrogen chloride, which when we put it in water becomes hydrochloric acid, very strong acid. It's the stuff in your stomachs. It is dipolar. Now, when it does mix with water, it's an acid because the hydrogen would rather go with an oxygen in the water molecule than stay around with the chloride. And the chloride just kind of hovers around near the new ion, the hydronium ion, which is H3O+. So the hydrogen says, sayonara to the chloride. I'd much rather be with oxygen. Chloride is fine with that. Chloride is fine being chloride. So it is dipolar. So if we have polar and polar molecules, then they will orient themselves based on an electric field, which is much like a magnetic field. You can make a magnetic field with an electric field, and vice versa. Especially if you move a magnet, you can create an electric field. This is the whole idea of power plants. Thank you, Michael Faraday. So, in any case, just read along with you here. When polar molecules are placed between oppositely charged plates, okay, positive and negative, then they become oriented with respect to the positive-negative plates. So here we have hydrogen chloride, and the hydrogen is slightly positive, so it points towards the negative plate. and the chloride is negative and it points towards the positive. Questions about the diagram? Now, there are much easier ways to test if an unknown molecule is polar or not, to see if it mixes with water or if it mixes with oil. And if it does with one and not with the other, then you know what it is. There are a few liquids, though, that are slightly polar that can mix pretty well with both. Again, there's a gray zone. Just like there's a gray zone between very polar and ionic, there's a gray zone between polar and nonpolar. But the idea is to learn the main zones, not the gray zones. So learn the three main zones, and the gray zones will take care of themselves. So on the other hand, though, the molecule's shape can affect whether the overall molecule is polar or not. So hydrogen chloride has a shape that's just two atoms. So it's, automatically, if they have different polar or electronegativities, the thing will be polar. But once you get three, then you have different possibilities for shape. Once you have three atoms, you can be linear, as carbon dioxide is. And so there is no reason why one end should be different from the other. But water also has three atoms, and it is polar. So what gives? What's the difference? The difference is the shape because of the geometry. If you remember to include the lone pairs, then the shape of water is going to be like a tetrahedron. The atoms don't look like a tetrahedron. There are only three atoms, so it just looks bent. That's the shape of it. But the geometry is tetrahedral around that central oxygen atoms. So there will be a polarity because both hydrogens will be one way and both lone pairs will be the other. Lone pairs are absolutely negative. Hydrogens are positive. It's a very, very polar molecule. Okay. And again, I disagree slightly with the book here, but the book is saying a very simple rule. If you draw the line at 2.0, then anything more than that will be ionic. Things less than that, consider very covalent. I'm saying the whole range from 1.7 to 2.0 is up for debate, and even slightly less than 1.7 may be ionic. So a lot depends on the size of the atoms. And this gets, beyond regular chemistry and into honors chemistry to figure out exactly what's going to be. So I'm trying to keep the rules simple. Metal and nonmetal will be ionic. Use the chart that is in your book to know the exact numbers as you're doing the exercises. But for the most part, anything in the top right-hand corner of the periodic table is going to be more electronegative than anything farther away from that. So your fluorine, your oxygen, your chlorine, very electronegative. You get farther away from that, your carbon, your hydrogen, phosphorus, it's going to be less electronegative, and there will be polarity. Okay. Now, once you've got these molecules, and the question so far, by the way, because we're about to shift. Okay, so shifting topics. Now we've talked about elements and their electronegativity. We've talked about how when they go together covalently, will it be covalent or will it be ionic? But once they're together, is the whole thing now, is the whole molecule going to be polar or nonpolar? Now we put more than one molecule in the same region. What's going to happen? How will they interact? What will those forces be? Forces are interactions, so as you put them together, they will either attract each other or they will repel. But what are they going to do? How can we predict it? So if we think about molecules and ionic bonds, we know that those things are stuck together. But molecules are easily melted. I should say covalently bound things like, let's say, butter or ice, things that have a covalent bond, they're easy to melt. But the bonds that are inside the molecules, the intramolecular forces, those are very strong. You can't break down water just by putting it on the stove. You can push the water molecules away from each other and become steam, but it's still going to be water. It may all be all over the windows in your kitchen. You know, if it's cold outside, you'll fog up the window, but it's still going to be water. Those intramolecular forces are much stronger than the intermolecular forces. Now, I'm not going to use intra very much. That just means within. If you hear me say inter and you wonder, is that inter or intra? Most of the time it's going to be inter, between the molecules. So they are weaker. And that's why a lot of covalently bound things, especially the nonpolar ones, are gases. Quite a few are liquids, even if they're light like water. And of course, many are solids as well, especially if their molecules are very, very large. Like in clothing, the molecules of cloth, if you look this up, it's incredibly huge. Okay, so let me just shrink this down just a little. Okay. Yeah, okay. So van der Waals was this fellow, and he talked about different forces, about what it is that makes things get together. The very weakest thing that makes molecules get together is simply that sometimes electrons are on one side of an atom instead of the other, and so for just the tiniest fraction of a second, one side of an atom is more positive and the other is more negative. And then the electron moves back. It's a very, very swift thing. But during that time, the universe still works, attractions still work, and so if that electron has gone to the far side, then the near side is positive, and some electrons may get attracted to that, just in that real split second. And so now two molecules are kind of stuck together. They are not bound together with sharing electrons, but they are kind of magnetically attracted to each other like ions are, but much weaker than ions are. And as a result, the molecules stick together. They're not one new molecule, but they are two that are kind of stuck together. It's very weak, and it's very easy to rip apart again. And they do this all the time. But you need to know that when we have these fancy words, dipole interactions, dispersion forces, that's what's happening. Just for the smallest, briefest time, these things these electrons are moving around, and the molecules stick together. All right, let's see here. I've said that, and so again, very briefly, you have that. Okay, it's very weak, very weak. So I'm going to just put in a word here. It's called London. It has nothing to do with the cities. This is a guy who's actually an American, so not even English. I think it's from North Carolina. I'm not sure. Anyway, he discovered the very weakest, which is what I've already mentioned about, where just having the electrons move to the other side, just for the splittest second, makes these molecules stick together. And then when the electrons come back, maybe they break up again. It can be that fast. Again, less than a tenth of a second. They're together, they're not together. All right, so take, for example, fluorine and chlorine. They are nonpolar, so they're not going to stick to each other like different molecules like water will stick to itself, but fluorine and chlorine will not. And so they're gases. Even though chlorine is pretty heavy, it's much heavier as a gas than water is, but water sticks to itself, and chlorine does not, at least not with polarity. So they're gases. Bromine, though, is really heavy. And because it's so heavy, gravity forces them down. And so they have no real choice but to stick together. But it's a liquid. It's a liquid. And last, iodine, which, following the pattern, should be iodine, but nobody ever says that, is actually a solid. But even though it's a solid, if you ever see a jar of iodine, You probably think, well, it's a liquid. That's because it's been mixed with water or something. But pure iodine is actually kind of a crystal, kind of like carbon can be a crystal of diamond, but worth a lot less. So you just drop a couple of crystals into some oil or something, and it swirls right up. And so it's a solid because it's so heavy. Well. All right. You have seen the homework. Many of you have done it. Thank you. Keep working on old stuff. Bye-bye. Thanks for the reminder, Caitlin.